I got a joke. You want to hear it?
Yes.
Okay. Why did the baby corn, or sorry, what did the baby corn say to the mama corn? Where's popcorn? Get it? Popcorn, pop. Come here, Nora. Come here, Sylvie. Look. Stand up on your chair. Look. What's going on here? Stand up on your chair.
Why do you got a pencil in there?
How come the pencil looks cracked? Is the pencil broken?
No.
Does it look broken to you?
No.
Look in the glass. It looks like it's split in half. Doesn't it?
Yes.
Yes. But if I take, it's not. Now it is. Holler it again. No, it's not. Now it is. No, it's not. Now it is. It's so on. It's so on. Okay.
No, I thought.
So that's refraction. That's the bent pencil effect, they call that. Interesting? Okay. There's an obvious example of light refraction in the middle of this picture. Generally, light will travel at a speed of around 300,000 kilometers per second, which is true in a vacuum and is almost true in air as well. So the light that's coming from the pencil that's in the glass, if we ignore the glass itself, is reaching our eyes at that high speed. However, the light that's traveling from the pencil that's immersed in the water is traveling slower as it's going through the water. Water will slow it down. However, when light enters the glass-water interface into the air, that's where the light will speed up again, and that difference in speed is the reason why you have that bent effect in the middle of that picture. It's kind of like if you were to go off the road in a car. One of the reasons why you can go off the road is when one wheel hits a soft shoulder, and that slowing down wheel amongst all the other three, which are maintaining their speed, is enough to cause that car to also bend in the direction that tire is slowing down, off and towards the ditch. So similar to here, how light will behave in air compared to a fluid. Our experiment in this video will focus on refraction as light goes through water and also oil to see if there's any difference in those two different fluids. So here you can see a beam of light coming from the ray box shining through our makeshift lens filled with water. Now a little less obvious is the refraction that's occurring, but it's clear that there is a bend in the light as it enters the water and as it leaves the water. So our first step is to trace the outside area of our lens filled with water, and then we'll shine an angle that's at around 45 degrees of light towards the right-hand side of this lens. The setup shows my angle of incidence at 45 degrees coming from the ray box. It also shows how I get that angle of incidence, much the same as in our mirrors. You need a normal line. That's a 90-degree perpendicular line that meets the lens's face. So now here, of course, the lens is not put into place. The light's coming straight on through. You can see it coming straight out the other side of the box. So that's kind of what would happen with zero refraction. No slowing down as it enters a medium that hasn't changed. So we'll see now what happens when we put the water. Here you can see the angle of incidence at 45 degrees in the top right-hand corner. As light enters this water-based lens, it refracts. Now you can't quite see it in the middle of the lens, but you can see it as it emerges. The light is definitely not on a straight path from where it entered. It's a little less fuzzy. We'll have to do some measurements. So tracing the emerging ray, which is in the bottom left-hand corner, I have a gap between. Obviously, I couldn't write in the glass, so we had to fill in that gap in between with the ruler and pencil. So here's the finished diagram with a bit of water on it, and also set up now to measure our angle of incidence. Not quite 45, it's coming at a 46-degree angle. The first refracted angle measures at 34 degrees. This is the incident ray as it emerges from the water-based lens. It measures at 33.5 degrees. And as this light refracts coming from the water into the air, it bends away from the normal line, and it bends away at an angle of 45 degrees. So just to recap, you can see that as light went from the low density air into the glass, it did refract towards the normal line at a 34-degree angle. And opposite, when it went from high density to low density, it refracted away from the normal line back to the 45-degree angle. So from the diagram's point of view, the angle of incidence at the top right-hand corner is 46 degrees. As light entered the water lens, it refracted towards the normal line at an angle of 34 degrees, just as we would expect. Again, light slows down as it enters water. Now, as it leaves water, the angle of incidence in the bottom left-hand corner is 33.5. So it's not quite the 34, and there's only pencil error that created that difference in the first place. But however, as light leaves that high density water and enters the much, much lower density air, it's going to now refract away from that normal line. And it did so at an angle of 45. Now again, in a perfect world, it would be a 46-degree angle, which was the same angle of incidence in the very first case. Now we'll compare this to oil and how light will refract through that substance. So to do the experiment in oil, it was pretty much repeated, except I obviously had to put oil into my plastic container. Now, I used the same angle of incidence in the first case as well, 45 degrees. And I think I did maintain that 45 degree. Now, the other clear thing in this photo, I think, is how much refraction is taking place compared to water. There seems to be a much greater difference in where the light emerges from the whole box on the left-hand side compared to water. To see these differences, again, we'll need to do some measurements. The first angle you can see is the angle of incidence. It's not 45, it's 46 degrees, but we can work with that. Now here you can see the refraction angle at 28 degrees, much more than what it was in water, indicating light must have slowed down more in oil than it did in water. Here you can see light emerging at roughly that same angle that it came in at 27.5 degrees. And as light emerges from the oil lens, it emerges and refracts at 45 degrees, so we're back to roughly how it entered. Just to recap, you can see that the angle of incidence for light as it traveled from air into the oil was 46, and it refracted as it entered the oil at an angle of 28 degrees. As it left the oil, it left at an angle of 27.5 and refracted away from the normal line this time at an angle of 45 degrees. So using our diagram, we can see the angle of incidence in the top right-hand corner is at around a 46-degree angle. Now, since it's traveling through air into oil, and oil will slow the light down, we would expect the light ray to now bend towards the normal line, which it did, at an angle of 28 degrees in this case. Now, since light is traveling at that angle, it should emerge at roughly that same angle, and did so at 27.5. Now, since light is leaving oil, a high optical density substance, into air, a low density substance, it's going to refract away. And you can see that it clearly did. And it did so at much the same angle as it did in the first place, but 45 degrees. So a little bit of error, not too bad. Optical density is not the same kind of density we discussed in the past for fluids. Optical density has to do with the molecules, and what we can clearly see here is that the oil is made up of molecules that really slow down light more so than water. Now water is H2O, we know that, and it's a small molecule where light can travel through it a little better than it can through oil, which is typically made up of many carbon and hydrogen atoms strung in long chains. So light will be slowed down more so in a substance of that nature. But as we remember probably, oil is much lower regular density than water. That's why oil will float on water. But optical density and fluid densities are not the same thing. The major use we have for refraction, of course, is through lenses. Here you can see a convex lens, which is actually doing the opposite as a convex mirror. This is causing the light rays to actually converge. Converging rays are required when you have far-sighted vision. Far-sighted vision has light that just hits and focuses behind the retina. So what you need to do is to converge that light so it hits right on the retina, and you will improve your vision. Now, if you have nearsightedness, the light that's entering your eye is focusing just in front of your retina. What would correct that is a concave lens. You can see a concave lens will diverge the light so that it focuses in the better spot right on your retina, and you'll start to see a clearer image as a result. So again, opposite to what a concave mirror does, it converges light. A concave lens diverges light. Do you want me to make this orange get bigger?
Yes.
Okay, come over. Okay, look here for a sec. Watch. I'm going to make this orange get large. Okay, I'm going to magnify it. Let's do it. Look how big it is. How come?
Because it's in the water.
It's in the water. The water is acting as some kind of lens.
Take it out.
It's refracting the light. It's magnified.
Take it out.
See? It's only its normal size.
Take it out.
Yeah.
My turn.
Dump it in. Oh. Nice. Now your hand is bigger too.
My turn.
Okay, come over where Nora is. Dunk it in. Wow.